Big Bang Theory is the leading cosmological explanation for how our universe began. It suggests that the universe started as an unimaginably hot, dense point roughly 13.8 billion years ago and has been expanding ever since. Contrary to common belief, the Big Bang was not an explosion in space, but rather an expansion of space itself. The timeline of the universe, the history of the Big Bang, is divided into several epochs or stages. 1. The singularity, time 0. All matter, energy, space, and time were compressed into a point of infinite density and heat, called a singularity. Our current laws of physics cannot yet describe what happened at this exact moment. 2. Inflation, 10 cubed to the power of 6 seconds. In a tiny fraction of a second, the universe underwent a massive growth spurt, expanding faster than the speed of light. This smoothed out the universe and determined its large-scale structure. 3. Nucleosynthesis, 3 to 20 minutes. As the universe cooled, protons and neutrons began to fuse. This created the first atomic nuclei, primarily hydrogen, 75%, and helium, 25%, with trace amounts of lithium. 4. Recombination, 380,000 years. The universe finally cooled enough for electrons to bind with nuclei to form neutral atoms. This made the universe transparent, allowing light to travel freely for the first time. This first light is still detectable today as the cosmic microwave background, CMB. The 3 pillars of evidence. The theory is supported by 3 major pieces of observational evidence. Redshift of galaxies. In the 1920s, Edwin Hubble observed that distant galaxies are moving away from us. The further away they are, the faster they move, proving the universe is expanding. Cosmic microwave background, CMB. Discovered in 1964, this is the afterglow of the Big Bang. It is a faint, uniform glow of radio waves filling the entire sky, representing the heat left over from the early universe. Abundance of elements. The observed amounts of light elements, hydrogen and helium in the universe, match the mathematical predictions of what should have been created during the first few minutes of the Big Bang. The fate of the universe. Because the universe is expanding, cosmologists look at 3 potential long-term outcomes. 1. The Big Freeze, heat death. The universe continues to expand forever. Stars run out of fuel, galaxies drift apart, and the universe becomes a cold, dark, empty void. 2. The Big Crunch. If there is enough matter, gravity eventually halts the expansion and pulls everything back together into a final singularity. 3. The Big Rip. If dark energy, the force-driving expansion, becomes strong enough, it could eventually tear galaxies, stars, and even atoms apart. Common misconceptions. It was an explosion. It was a rapid expansion of space. There was no outside or empty room for the Big Bang to explode into. Space itself was being created. It happened at a specific spot. Because space itself expanded from a point, the Big Bang happened everywhere at once. Every point in the current universe was once part of that initial singularity. The history of the universe is generally divided into several eras based on the dominant physical processes occurring at the time. From the initial expansion to the cold, distant future, the universe evolves through stages of decreasing temperature and density. 1. The very early universe, the primordial era. This period covers the first few minutes after the Big Bang. Things happened at nearly instantaneous speeds. Planck epoch, 0 to 10 to the power of minus 43 seconds. The earliest period of time. Our current physics, general relativity and quantum mechanics, cannot describe this era. All 4 fundamental forces were likely unified. Inflationary epoch, 10 to the power of minus 36 to 10 to the power of minus 32 seconds. The universe underwent an exponential expansion, growing from smaller than an atom to roughly the size of a grapefruit in a fraction of a second. Quark epoch, 10 to the power of minus 12 to 10 to the power of minus 6 seconds. The universe was a soup of quarks and gluons. It was too hot for these particles to bind together into protons or neutrons. 2. The early universe, the plasma era. As the universe cooled, matter began to take its familiar forms. Nucleosynthesis, 3 minutes to 20 minutes. The temperature dropped enough for protons and neutrons to fuse, creating the first nuclei of hydrogen, helium, and a trace of lithium. Photon epoch, 10 seconds to 380,000 years. The universe was a dense, opaque plasma. Light could not travel far because it was constantly bumping into free electrons. Recombination, 380,000 years. Electrons finally bound to nuclei to form neutral atoms. The universe became transparent, and the first light traveled across space. This light is visible today as the cosmic microwave background, CMB. 3. The Dark Ages and the Stellar Era. The universe moved from a featureless gas to a structured cosmos. The Dark Ages, 380,000 to 150 million years. No stars had formed yet. The universe was filled with dark hydrogen gas and the fading glow of the CMB. Reionization, 150 million to 1 billion years. Gravity pulled gas into clouds, igniting the first stars. Population 3 stars. Their intense radiation stripped electrons back off hydrogen atoms, clearing the cosmic fog. Galactic evolution. Small star clusters merged to form the first proto-galaxies, eventually leading to the massive spirals and ellipticals we see today. 4. The present day, the Stelliferous Era. We are currently living in this era, which began about 1 billion years after the Big Bang. Star formation. Most of the universe's energy is produced by nuclear fusion inside stars. Dark energy dominance. Roughly 5 to 6 billion years ago, a mysterious force called dark energy began to overpower gravity, causing the expansion of the universe to accelerate. 5. The future eras. Physical eschatology. Based on our current understanding, the universe will eventually run out of energy. The degenerate era. 10 to the power of 14 to 10 to the power of 40 years. Star formation stops. The universe is populated by dead stars, white dwarfs, neutron stars, and black holes. The black hole era, 10 to the power of 40 to 10 to the power of 100 years. Only black holes remain. They slowly evaporate through a process called Hawking radiation. The dark era, 10 to the power of 100 years. After the last black hole evaporates, only low-energy photons and neutrinos remain. The universe reaches its final state of maximum entropy, known as heat death. The most common way to categorize advanced civilizations is the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. This scale measures a civilization's level of technological advancement based on the amount of energy they are able to harness and use. The original Kardashev scale, the scale originally consisted of 3 types, though scientists have since expanded it to include theoretical supercivilizations. Type 1, planetary civilization. A Type 1 civilization can harness all the energy available on its parent planet. Energy source: total solar, wind, thermal, and potentially fusion energy. They have complete control over their planet's climate, weather, and geological forces, like earthquakes or volcanoes. Where are we? Humanity is currently a Type 0 inches civilization. Carl Sagan estimated we are at about 0.73, as we still rely heavily on dead plants, fossil fuels, rather than the planet's total energy output. Type 2, stellar civilization. A Type 2 civilization can harness the total energy output of its parent star. Energy source. The most famous theoretical method is the Dyson sphere, a massive structure built entirely around a star to capture its radiation. Capabilities. They are essentially immortal. No known natural disaster, like a nearby supernova or a massive asteroid, could wipe them out, as they could simply move their planetary system or block the radiation. Type 3, galactic civilization. A Type 3 civilization can harness the energy of an entire galaxy. Energy source. They would capture energy from billions of stars, black holes, and the galactic center. Capabilities. They would have mastered interstellar travel and communication. To us, their technology would appear indistinguishable from magic. They might use black hole engines or manipulate the fabric of space-time for transport. Theoretical extensions. Type 4 and beyond. While Kardashev stopped at Type 3, modern theorists have speculated on even higher tiers of existence. Type 4. Universal civilization. This civilization can harness the energy of the entire universe. They would likely be able to manipulate the expansion of space, change physical laws, and live inside or near supermassive black holes across all galaxies. Type 5. Multiversal civilization. a civilization that has moved beyond its own universe and can harness the energy of multiple bubble universes. They would be capable of creating new universes with specific physical constants, like different gravity or speed of light. Type 6, multidimensional/godlike. At this level, the civilization exists outside of time and space as we know it. They could manipulate dimensions beyond the standard 4, 3D space plus time, effectively becoming the architects of reality. Alternative, the Barrow scale. While Kardashev looks at how much space a civilization can control, physicist John Barrow proposed a scale based on how much smallness they can control. Micro-dimensional mastery. Type 1-, manipulating objects larger than themselves, building structures. Type 2-, manipulating genes and cells, biological engineering. Type 3-, manipulating molecules and atoms, nanotechnology. Type 4-, manipulating individual electrons and nuclei, subatomic engineering. Type 5-, manipulating elementary particles, quarks and gluons. Type Omega-, manipulating the basic structure of space and time itself. Cosmic redshift is the phenomenon where light from distant objects in the universe is stretched to longer, redder wavelengths as it travels through space. It is the primary tool astronomers use to measure the distance of galaxies and the rate at which the universe is expanding. How it works. The stretching of light. Light travels in waves. The color of light is determined by its wavelength. Blue light has short, high-energy wavelengths. Red light has long, low-energy wavelengths. When a galaxy moves away from us or when the space between us and that galaxy expands, the light waves are literally stretched. By the time that light reaches our telescopes, it has shifted toward the red end of the electromagnetic spectrum. The three main types of redshift. While the result looks the same, the causes can be very different. 1. Doppler redshift. This is caused by the local motion of an object through space. It is identical to the Doppler effect we hear with sound. A siren sounds higher pitched as it approaches and lower pitched as it moves away. If a nearby galaxy is physically moving away from the Milky Way, its light shifts to the red. 2. Cosmological redshift. This is the most important type for understanding the big picture. It is not caused by galaxies moving through space, but by space itself expanding. As the fabric of the universe stretches, the light traveling through it stretches as well. The further away a galaxy is, the more space there is to expand between us. Therefore, more distant galaxies have a higher redshift. 3. Gravitational redshift. This occurs when light tries to escape a strong gravitational field, like that of a black hole or a massive galaxy. As the light climbs out of the gravitational well, it loses energy, which causes its wavelength to stretch and shift toward the red. Measuring redshift. Z. Number. Astronomers use the variable Z to represent redshift. It is calculated by looking at the spectral lines of elements like hydrogen or helium. Since we know exactly where these lines should appear in a laboratory, we can measure how far they have shifted in light coming from a distant galaxy. Z equals 0. The object is not moving relative to us. Small z, e.g. 0.1. A relatively nearby galaxy. High z, e.g. 10 or higher. These are the first galaxies that formed shortly after the Big Bang. Why is it important? 1. Hubble's law redshift allowed Edwin Hubble to prove that the universe is expanding. He found a direct mathematical relationship between a galaxy's distance and its redshift. 2. Looking back in time. Because light takes time to travel, high redshift objects are also the oldest. Seeing a galaxy ATZ equals 11 means we are seeing it as it looked over 13 billion years ago. 3. Mapping the large-scale structure. By measuring the redshift of millions of galaxies, researchers have created 3D maps of the universe, revealing the cosmic web of filaments and voids. 4. Dark energy. In the late 1990s, observations of redshift in distant supernovae revealed that the expansion of the universe is actually accelerating, leading to the discovery of dark energy.